This is part 2 of the lecture on nonlinearity. At the end of part 1, we studied how to work with a nonlinear relationship by converting the numerical independent variable to an ordinal scale categorical variable. Another important and widely used method for working with nonlinear relationships is the mathematical conversion of a variable. There are various mathematical forms that a variable x can take. Here are just a few of them. By replacing x with a mathematically converted form of x or including a mathematical transformation of x in addition to the original x, we may be able to capture the nonlinear pattern. Then, what mathematical form should we adopt? Sometimes, a certain mathematical form may be derived from some theoretical inference or prior knowledge. Other times, we explore and find an appropriate form by trial and error. Note that we can still use a computer program for linear regression, because the mathematically converted form of x can be treated just like any other independent variable. A good starting point of such an exploration is the quadratic function, which could be produced just by including x squared as an additional independent variable. Sometimes, this could substantially improve the goodness of fit of the model to the data. An advantage of the quadratic function is, it can produce 6 common patterns of nonlinear relationships, as shown in this graph. Those patterns are, starting from the upper left panel to the right, upward and concave, downward and concave, downturn or inverse U-shaped. From the lower left panel, we have upward and convex, then downward and convex, upturn or U-shaped. A large portion of nonlinear relationships we come across in health science and social science research follow one of these 6 patterns. But if the pattern is more complicated with ups and downs, or shifts between concavity and convexity, the quadratic function cannot be fitted to the pattern, and a more complicated mathematical function should be tried. Making use of the quadratic function, regression models of systolic blood pressure and BMI were set up as shown here. x1 to x5 are binary dummy variables for race, ethnicity, and education, x6 is age as a numerical variable, and then, age squared is included as x7, which is age times age. Be careful not to replace age with age squared, but include age squared in addition to age. In this case, we are adding the age squared term. Results of the regression analysis of systolic blood pressure are shown here. Note that the partial regression coefficient for age squared was relatively small, 0.001, and its p-value was high, 0.678. Therefore, the results seem to suggest that the age squared term may not be necessary. This is not surprising because the plots that we saw earlier indicated the relationship between systolic blood pressure and age was quite linear. We probably don't need to introduce a nonlinearity term into the model. But results of the regression analysis of BMI are quite different. The partial regression coefficient for age squared was negative 0.003, which seems relatively small, but its p-value was very low, 0.002. Thus, the results seem to suggest that the age squared term surely improves the fit of the model to the data. This is the relationship between BMI and age, implied by the estimated values of partial regression coefficients for age and age squared. It looks parabolic. So, according to this model, BMI tends to increase in middle age, reach a peak near age 60, and then begins to decrease. Does this make a physiological sense? Probably it does. In middle age, accumulation of body fat may gradually increase the body weight. But bone density, and muscle size tend to decline among many old persons, reducing their BMI. By the way, the regression model included race, ethnicity, and education. The model implies that this parabolic pattern remains the same for all combinations of race, ethnicity, and education categories, but the curve makes parallel shifts upward or downward, depending on the effects attributed to race, ethnicity, and education. This graph was made for those who belong to both reference categories, that is, college graduates who are non-Hispanic white. Now, if the age squared term was important, why was its regression coefficient small, like minus 0.003? This is because age squared tends to be a big number. For example, if age is 50, age squared is 2,500. But systolic blood pressure is on a smaller scale. Its mean value may be around 120 to 130. Since variations in systolic blood pressure are on a much smaller scale than variations in age squared, the coefficient was adjusted for the scaling difference. By converting x mathematically or to an ordinal scale, we may still be able to use linear regression to deal with nonlinear relationships. But sometimes it is impossible to produce a linear combination form by such a conversion. For example, this is a mathematical model of adult mortality, proposed by an actuarial scientist Wilfred Perks in 1932. Here M of X denotes the death rate at age X. Perks claimed that this four-parameter logistic model captures age patterns of adult mortality very well. It is difficult to linearize this model by mathematical conversion. In such a case, we resort to using a nonlinear regression which directly takes this equation and fit it to data by a sort of trial-and-error algorithm. Earlier in this session, we studied conversion of X for dealing with nonlinear relationships. But sometimes conversion of Y may be effective. For example, this is a plot of the death rate by age that we saw earlier in part 1 of this session. The relation between death rate and age is certainly nonlinear. In this example, a mathematical conversion of Y, which is death rate, successfully linearizes the relationship. Logarithmic conversion of Y was adopted, that is, log Y, instead of Y, was used as the dependent variable. Note that if Y is considered as an exponential function of the linear combination of X's plus residuals, then log Y should be a linear combination of X's plus residuals. This is a plot of the death rate by age again, but the death rate is on the log scale. The curve appears quite linear between age 30 and 90. This is a plot of the death rate by age, between ages 30 and 90. Now the death rate is back on the original scale. The graph shows an accelerated increase in death rate with age. This is a plot of the log death rate by age, between age 30 and 90. The pattern is very linear. Results of linear regression of log death rate on age, between age 30 and 90, are shown here. R-square was 0.998, almost perfect. The regression coefficient of 0.089 implies that among U.S. women between age 30 and 90 in year 2000 to 2004, the death rate increased with age at the rate of about 9% per year of age. Finally, it should be noted that importance of examination of linearity is not limited to linear regression, although the examination is most straightforward in the case of linear regression. Linearity should be checked for each numerical independent variable in any type of regression model.